This figure shows the relationship between extent of activation, in other words, the rate of the reaction, and directing effects, and does this by looking at specific groups. Now, most students' reaction when they see this thing is, oh my God, do I have to memorize the whole thing? And the answer is always no, you don't have to memorize the whole thing, because, for example, I'm never going to ask students the relative rates of these two, or the relative rates of, these two, for example. However, this is spring 2020 when this is being prepared, and in spring 2020, due to the response to the COVID-19 virus, the tests are being administered online, the whole course is being administered online, and as a result, it's open book and open notes, and yes, you can look at this thing. At any rate, let's take a look at it. So what we want to do is try to systematize what makes something, say, strongly activating versus moderately activating, or moderately deactivating versus, say, strongly deactivating. So in the event that you're ever, say, trapped on a desert island and you have to do this without looking at my colorful chart, you'll be able to do it. So let's start by looking at the strongly activating. But first, I just wanted to point out, again, all activators are orthopara directors, all meta directors are deactivators, and then we have the halogens, which are weakly deactivating, but also orthopara directors. They're kind of the anomaly here. So if we take a look at all of these, again, strongly activating groups, what you notice is that in each case, there is a heteroatom directly attached to the ring, and that heteroatom has a lone pair. We've got oxygen, we've got nitrogen. In fact, we've got oxygen and nitrogen and nothing else. So oxygen, oxygen, nitrogen, nitrogen, nitrogen. If we compare that to the group of compounds that are moderately deactivating, let's leave that ether aside for the moment. Again, we have lone pairs directly on the atom that's attached to the ring, but now in each one of these cases, except for the ether, there is an electron withdrawing group. Oops, that was a bad choice. There is an electron withdrawing group, the carbonyl, and so what happens is that the lone pair is trying to donate electrons towards the ring at the same time that the carbonyl is pulling them away. So as a result, this oxygen, this nitrogen, and this nitrogen are not as electron donating as the groups up on the top. And then we do have a slight issue here that if you have, as opposed to an OH or an amine, you have an ester, this gets put in this moderately activating group. And I tell students in a normal semester that they don't need to memorize that. In other words, I'm never going to ask you to compare phenol to anisole or aniline to anisole, or for that matter, phenol to aniline. So aside from the anisole or the aryl ethers, in each case, we have oxygen and nitrogen heteroatoms that are adjacent to these carbonyls. So notice carbonyl went away, no carbonyls. All right. Then if we move on to the last set of activators, if you wanted to look for a commonality with all of these, you could say that in all cases, they have an alkyl-based group, or maybe even a better way of saying this is that they have a hydrocarbon group, in other words, carbon and hydrogen only, attached to the benzene ring, and those are weakly activating. And again, benzene is our reference point. It's neither activating nor deactivating, and it can't be really directing, although I guess I should have just left that colorless or white. And so if we go back to these, let's see, we have kind of weakly activating, we have moderately activating, and we have strongly activating. And I really don't care how you think of these things with emoji or whatever. So now if we look at the next group down, the ones that are weakly deactivating, those are halogens. There was really no other way to look at that. Those are halogens except fluorine. So we need a new color. So the commonality between those three is that they're all halogens. So now if we turn to the moderately deactivating groups, and you look at these, in nearly all of the cases, certainly for these 5, what you have is a carbonyl acting as an electron withdrawing group that's right next to the ring. So again, carbonyl right next to the ring. And remember that these carbonyl groups are going to be electron withdrawing groups. You can even draw a second resonance contributor just for the carbonyl, where you put a positive charge on the carbon and a negative charge on the oxygen. Or just drawing these, for example, with the ketone here, you could say that there's a slight positive charge on the carbon, a slight negative charge on the oxygen. And then turning to these other two, you have a similar situation. You can take those electrons and pull them towards the nitrogen the same way you could with the carbonyls, and then the same with this sulfur group. So in all of these cases, if you're looking for commonalities, you have an atom directly attached to the ring that has a double bond. In each case, the double bond is to some sort of a heteroatom so that you can draw these resonance contributors that I showed with the curved red arrows. And then finally, we have our group of strongly deactivating. I don't know if I have a harsher color than red. Orange, not really. All right. So with these strongly deactivating groups, if you ignore the one on the far right for the moment and you just look at these two, what you see here is that you have a full positive charge on the atom that's directly attached to the ring. And that's going to be more deactivating than having the partial positive charges that we had up here. And then you have this scenario where you put several halogens on the atom that's directly attached to the ring. So, and here is the nitro group that is basically the poster child for being an electron withdrawing group and extremely strongly deactivating at the same time. And so I guess we need to get out the emoji again. So we have strongly deactivating, we have moderately deactivating, and then I'm running out of emoji on this. That one just looks angry. With the halogens, we have, I don't know, very slightly deactivating compared to the one up there. So again, the trick, should you ever be in a situation where you need to memorize these, is to look at the commonalities between each one of these sets. Lone pair, no carbonyl. Lone pair next to a carbonyl, except for that. Hydrocarbon group, halogen, carbonyl or other atom attached to, with a double bond to a fairly electronegative atom. And then with this group we have, except for the one, the trihalogen one, we have a full positive charge, which is going to be more withdrawal